Repeating the trend of transition metal, we're now going to compare the difference in characteristic between an S block and a D block element. So the S block element over here, representative is going to be your calcium, and for the case of vanadium, this will be representative of the D block elements. So which of the statement here is actually true with regards to density? And in general, the density of D block elements is considered to be more dense than that of your S block elements. So in vanadium itself, it has a total of 23 electrons, and for the case of calcium, it has a total of 20 electrons. So writing out its electronic configuration, for vanadium, we have argon that constitute 18 electrons in that config. So with 5 more to fill up, we're going to take a look at us putting a 4s2 and a 3d3. Now for the case of calcium, it will be argon with 18, and the remaining 2 will be in the 4s2. So I will have to disagree with option 2 to say that vanadium has a greater number of outer shell electrons than calcium, because for both of them, the biggest principal quantum shell is 4, and the valence electrons for that is actually 2. They all have the same number of valence shell electrons. But if we were to just break it down slightly further, in argon, this is that of a 1s2, 2s2, 2p6, 3s, 2, and 3p6. So the shielding effect here is actually going to be much lesser in vanadium as compared to that in calcium, because the shielding of 4s2 in calcium is actually shielded with the 3p6 subshell that has a total of 3 sublevel, 3px, 3py, and 3pz from the nucleus itself. And because of that, I'll say that if it's less shielded, the forces of attraction is feeling from the nucleus is also going to be much lesser. So with a much lesser forces of attraction, I'll say that the valence shell is actually considered to be further. And if it's going to be much further, that would mean that in the same volume itself, we can actually have much bigger calcium atom. You can actually fill up lesser calcium atom in the same space. But for the case of your vanadium, the 4s2 electrons is actually being shielded by your 3d subshell. And 3d itself has a total of 5 sublevel. You have your 3d xy, 3d xz, 3d yz. The excited sublevel will be inclusive of 3d x2 minus y2 and 3d z2. Since this is a much more diffuse subshell, I'll say that the forces of attraction that is being felt by 4s from the nucleus is going to be much stronger, because it's much wider spaces in 3D. So the nuclear charge from the nucleus itself will actually be felt much stronger. And if it was actually felt much stronger, this will actually result in the valence shell to be closer to the nucleus. So each of the vanadium atom is actually going to be extremely compact. So in the same volume itself, the number of vanadium that I can hold is going to be much more as compared to the number of calcium atoms that I can actually hold. And because of this, in the same volume, having more mass means that it's actually going to be much more dense, and it's because of the more diffuse 3D subshell that actually does minimal to try to prevent the nuclear charge of the nucleus from actually reaching the valence shell. And therefore 3 is the only correct answer for this question, and D is the answer that we are looking at.